Hi everybody! In this video, we will create a shader that displays a grid. It may sound simple, but such a grid is a very useful element, whether for debugging or its use in various effects. Let's get started. If shader programming is something new to you, it would probably be useful to first say a few words about the fundamental difference compared to regular screen drawing, as we are used to from other languages such as GDScript. In GDScript and the Godot engine, if we want to, for example, draw a sprite at specific coordinates, we simply place that sprite in the editor or set its position in the script and let the Godot engine take care of the rest. Nothing like that works in shaders. In the book of shaders, there is a great comparative image that I'm showing right now. In the upper part, we have the CPU equivalent, which processes instructions through a single pipeline, while the GPU in the lower part is equipped with a specific pipeline for each pixel on the screen, so the instructions are processed in parallel and much faster. So, in the shader code, we only have the fragment function for drawing, and the function is called in parallel for each pixel, and its output is only the color of that pixel. In other words, instead of drawing a line from point A to point B, we must calculate which pixels the line between points A and B would contain and set their color. And that's exactly what we'll do now when creating our grid, calculating the grid pixels and coloring them. I will show you two ways to add such a simple square grid to the shader. One way utilizes fractional parts of float numbers, the other works with trigonometric functions. Let's start with the first one. So, as usual, I begin with creating the scene, color rect, and material with shader. Let's do it here, right-click, create new scene, and call it grid. Okay, now right-click, add child node, and color rect as usual. Let's fix its dimensions. So we set it to 600 by 400. Scroll down to the material. Let's create new shader material. Click add new shader, grid GD shader, canvas item. This is correct. Just a folder. We will change it to shaders and create, and click again to open in the editor. Okay. So shader is ready. We can write a skeleton of our effect. As usual, we will just get rid of the vertex function, so we don't need it, and nor the white function. Alright, we'll be drawing a grid, so let's create a function that would contain our code. Float, draw grid. The reason it returns float is that we will simply return the color of the particular point, and if it belongs to the grid, it will contain some non-zero value, otherwise it would contain 0 as black, and the input parameter is vector2 UV coordinates. Let's start with something very simple, so I will simply define vector2 grid UV and assign just UV to it for the time being. And we will return something, and of course we want to return float, not a vector2, so we can, for instance, return the x coordinate. Okay, and now the fragment function. We will move the origin from the top left corner to the center, so we need to subtract 0.5 and define the color of this particular pixel, which is vector3 for RGB components, and it would just contain the result of this function draw grid, this parameter UV. And since we are using only one parameter of vector 3, it means that all three components would have the same value, which would result in a shade of gray. And finally, it needs to be assigned to the internal value color, which is vector 4, because it contains the alpha value as well. So we add color and let's set it to opaque. Very well, let's take a look. So far, this doesn't give us a particularly impressive result. Let's keep in mind that we are working with UV coordinates, whose origin has been shifted to the center. So both vertically and horizontally, we move within the range from negative 0.5 to 0.5. Negative 0.5 to 0.5 and 0, 0 is in the center. And anything less than 0 will automatically be displayed as 0, which is a black color. If we want to create a grid, we need some periodic function. As I mentioned at the beginning, one option is to apply the fract function, which returns the fractional part of a number. Let's give it a try. So here, instead of UV, we will use fract UV. And how does it look? Okay, something has changed. And in these negative coordinates, we no longer have just a black color. But why does the resulting value tend towards the white color as it gets closer to 0? This is due to the implementation of the frac function, which actually works like this. Let me open the graph editor, and the implementation looks like x minus floor x. Okay, and this is exactly how GLSL and Godot shading language works with the fract function. If we just enlarge it, we can see that in our range from minus 0.5 to 0.5, it goes from here to 1, which is the white color, then switches back to 0, black color, and goes up. So this is exactly what we can see here. Before we move on, let's give our future grid a nicer color. We will add a uniform parameter called line color and use it to colorize the output of the fragment function. So I'll put it here, for instance, uniform vector 3 line color, and it is source color, so we will get this nice color picker in the inspector, and let's give it some initial value, vector 3.2.3.5. Okay, and what we need to do now is to multiply our color by this line color. My line color. It should change color now. Yes, it works. And since we are already multiplying with a vector 3, we no longer need to create vector 3 out of this result of the drawGrid function. Okay, because multiplying float by vector 3 is vector 3 again. We just multiply all components of the vector with the same value. Now, we need to ensure that we are not only returning values from vertical lines, but also horizontal ones. Otherwise, it wouldn't be a grid, of course. So what happens if we use y instead of x here? Yeah, it's horizontal. And to combine both, we can either call this function twice, which wouldn't be a very efficient solution, or return the maximum value from both components. This way, we'll ultimately get both simultaneously. Let's do it. So it would be max grid UV x, grid UV y. And wait for it. Yeah, here it is. So what's next? We have a hint of the future grid here, but we are somewhat bothered by the color gradient that we'd like to remove. For this, the functions step or smooth step are best suited. Let's try step first. As we can read in the documentation, the step function with parameters edge and value returns 0 for all values less than the edge and 1 otherwise. Therefore, it's necessary to set the edge very close to 1 to make the resulting line sufficiently thin. let's do it right here. So we will just wrap draw grid in the step function and put the threshold to 0.99 and bracket. Okay, nice. The result looks nice, but we already see the first issue. The vertical line is slightly thicker than the horizontal one. This is because we are working on a rectangle and haven't addressed the aspect ratio, which we usually handle right at the beginning, as you may know from previous videos. Let's fix it now. So I will add uniform vec2 resolution and set it to our dimensions of our color rect, which is 600 and 400. Okay, and we need to use it, of course. We'll do it here. UVX is multiplied by the ratio resolution X divided by resolution Y. Y. Okay, wait for it. Yes. This is how we wanted to have it now. Let's get back to 100%. So, the step function is certainly useful, but if we leave the lines with such sharp edges, as you can see, there could be problems later when we have more of them and apply additional transformations, such as scale or rotation. Instead of step, we will use smooth step. It works very similarly, but defines two threshold values and performs some smoothing of the result. Let's change it here, so it would be smooth step, and the second parameter will set to 1. Wait for it. Okay, if we zoom in, we can see that it is smoother, and the transition from black to blue is more gradual. However, zooming in reveals also that it's slightly asymmetric, can you see it here? Which is caused by how the frac function calculates the resulting value. It won't be as noticeable with thin lines if I just get back to 100%. However, if we wanted to address this issue, it can be done using the second method I mentioned at the beginning. Instead of fract, we will use a trigonometric function, specifically cosine. But before we do that, let's finally display a real grid instead of just two perpendicular lines. We will add a new uniform parameter called zoom, which will then multiply by the UV coordinates in the fragment function. Let's get back to the uniform parameter section, uniform float zoom, and we'll give it a hint range so we can easily change the values in the inspector. And let's start at 1 and let's go to 50 by 0.1 step, and the initial value would be, for example, 20. And now we need to use it here, multiplying the UV coordinates by the zoom factor. Wait. Okay, as we can see, we see nothing. This is because the range values of the smooth step function remain constant, causing these artifacts. Like if I zoom in, you can see that something is being displayed, but not always, and it's just not good. So we need to ensure that the resulting line thickness adapts to the current zoom factor. We will do it like this. Let's add another uniform parameter here called thickness, uniform float thickness, and again with a hint range that would go from 0.1 to, for example, 10, and step is 0.1, this is correct, and start at 2. And we need to calculate it here before we assign color. So float line thickness would be zoom multiplied by thickness, and because we are working on the rectangle, we need to use the resolution y, which is shorter than resolution x, to divide the result by, okay, line thickness. And we will, instead of the constant 0.99, we will use line thickness that would be simply subtracted from 1. Okay, wait, now we have a nice, beautifully regular grid. If it seems too dark to us, we can change its color or multiply the result by some additional value, which we'll call brightness and add as a uniform parameter. Okay, again, and it's again a float, so I will just copy paste here to save time. Brightness, and the hint range, let's make it to 4 only, otherwise everything would be just white. And we will multiply the final color by brightness. Okay, yes, it's brighter. Let's take a look at the parameters. Everything is here. Alright, let's go back to improving the drawGrid function. As I said, instead of fract, here it is, we will now use cosine. Let's try it. It seems that the zoom factor has changed slightly. Well, not slightly, but it changed, of course. This is because the period of the cosine function is not 1, but double pi, which is approximately 6.28. We can demonstrate this again on a graph. Let's get back to here and show how the cosine, what did I do? Yeah, cosine x. Okay, so the period is right here, as I said, 2 pi, 6.28, but we want to convert it to 1. So we need to multiply the argument by 2 pi. 2 pi. Is that correct? Sorry. Yeah, this is correct. And now we can see the period is as we wanted that, 0, 1, 2, 3, and so on. Perfect. Let's do it here. Okay, and we already have a predefined constant in Godot shading language. It's called tau, and it's exactly 2 multiplied by pi, and we have our original grid back. So if we increase the zoom factor, we can see it's beautifully symmetric. Perfect. Very well. What else could we do with our grid? Let's try to come up with a simple animation that would perform translation, rotation, and scaling. I will start with translation. So the translation is simple. We just need to add something to UV, and something should change over time. So we will do, for example, this modification. Add a vector 2, and the x-coordinate would be sine of time, and let's make it a little bit slower, multiply by 0.4, and the second one, cosine time, crap, again, multiplied by 0.6. How does it look now? Something is wrong, sorry. Yeah, it shouldn't be here, this bracket. Okay, it's moving, and it's moving periodically. Very well. For the rotation, we need to define a rotation matrix. It looks like this. I will make another function which returns vector 2. Let's call it rotate, and takes a vector 2 UV coordinates and float as the angle of the rotation. I think I already used it before in previous videos, but let's do it again. It's very simple. We will return UV multiplied by matrix 2, which contains 2 vectors 2, vec2, which is a rotation matrix in 2D plane. Start with cosine of angle, then sine of negative sine, sorry, angle. This is the first vector. And now the second one, vector 2, sine, angle, and cosine, angle. Sorry, wrong arrow here. Is it correct? Yes, it is. Now we need to apply this transformation after translation, which is here. So we will simply assign the rotation function result to uv. And uv and angle again would change over time. Let's make it time multiplied by 0.1 so it doesn't rotate too fast. Yeah, it rotates. And finally, let's do scaling. We have the zoom parameter, but it's a uniform parameter, which means the value cannot be changed. Therefore, we'll temporarily comment it out and implement it again in the fragment function. Let's do it here. Float zoom would be, let's make absolute value, equals absolute value of sine of time multiplied by 0.5, again a bit slower, and multiplied by 40. Wait for it. Okay, now it's zooming, rotating, and translating. Absolute value is here because the sine values go from -1 to 1, and we don't want negative values here. So now it goes from 1 to 0 back to 1, and it's just a nice period. Very well, that should be all. So now we are really done. I think the video is long enough and we've managed to cover the most important things related to creating and transforming the grid. If you enjoyed it, I'd really appreciate every like and subscribe. So have a great day and see you in the next video.